Welcome back to Mr. Hassan's Maths channel. I'm now going to be answering this question, which is from a C34 paper from June 2020, and this is a specification which was before the P3 and P4 specification we have now, and it includes material from P3 and also from P4. Okay, so this is a question to do with integration. Now, before, integration was not in the P3 syllabus at all. There was no integration at all in it. But now there is some integration, and this is an example of one of the types of integration questions you will find now in the new P3 syllabus. So I'm going to save this part of the question and the second part of the question, which is also dealing with integration of trig functions, but that will also be saved for or under the P3 in my P3 material, and the part 3 is integration by substitution, which is in P4 basically. So I'll save that as a separate video. So I'm going to save these two as one video, and part 3 as a separate video, so I can save it under the P4 topic questions. So because I like to save my questions by topic and by paper. All right. So now let's get on with it. So this question here, you want to integrate with respect to y the expression 4 over 5y minus 7 to the power of 4. All right, so now what we're going to do here is I'm going to rewrite this so that this bracket, with the variable is written on the numerator. So I'm going to rewrite it as the integral of 4 times, then you have 5y minus 7 to the power of negative 4 dy. So they're the same thing. This is the same as that. Right, now it's in a form where I can integrate it. Now, what you've got to look for when you're integrating something like this is we're going to be using what's called the reverse of the chain rule. Okay, so you see, whenever you see like a function within another function, like here we have the main function here is something to the power of negative 4, and inside it is another function in terms of y, which is 5y minus 7. That's inside the function. Whenever you see that kind of situation, when you see a function inside a function, like for example, let me say f of gx. So there's a function inside another function. If you can see that the main function is multiplied by something or in the same order as the differential of what's inside the function, so if you can see that the whole thing is multiplied by something which is in the right order of the differential of what's inside the function, then you can use what's called the reverse of the chain rule. Okay, so we see that inside this function you have 5y minus 7. If I differentiate that with respect to y, I get 5, which is a constant. What's multiplying the whole of this? 4, which is a constant. All right, if this said 4y, for example, I wouldn't be able to now proceed. Or if you said 4y squared or something else, but because it's a constant and the differential of what's inside this function is a constant, I can use the reverse of the chain rule. I can use the reverse of the chain rule. All right. So how do you use the reverse of the chain rule? People do it in lots of different ways. The way I like to do it, to make sure that we're on the right tracks, is I like to write this out like 4 times, as it is, 4 times 5y minus 7. Now, what type of function is being integrated? Well, it's just like a polynomial, something to the power of something. So how do you integrate something like that? Well, you add 1 to the power. So I'm going to add 1 to the power. So that's going to become minus 3. And then divide by the new power. That's how you integrate such a thing of this form, or a polynomial. You add 1 to the power and divide by the new power. Okay, and then I also have to multiply, because we're using the reverse of the chain rule. I have to multiply by the differential of what's inside this function in the denominator. So I have to divide also by the differential of what's inside the function. So I multiply the denominator by, or you can say divide the whole thing by, the differential of what's inside the function. What's the differential of 5y minus 7? Well, it's 5. If I differentiate 5y minus 7 with respect to y, I get 5. And that gives us our answer, but don't forget the plus c. So we can say this is going to be negative 4 over 15 times 5y minus 7 to the power of negative 3 plus c. And that's the answer. And that's our answer. That's how you use the reverse of the chain rule to do integration. Now, how can we make sure in the exam that we've got the right answer? We don't have a mark scheme. Well, we know that we know that the differential and the integrals are inverses of each other. So if I was to differentiate what I found, if I was to differentiate this, what I've just found, it should give me what we started with. So let's differentiate this. If I differentiate this, I'm going to use the chain rule. So I'll multiply by the power. You see the main function is something to the power of something. So I multiply by the power. So I have minus 3 times minus 4 over 15. Okay, and then I'll have 5y minus 7. Then I have to take 1 away from the power, so that becomes minus 4. And then I have to multiply by the differential of what's inside the function because we're using the chain rule. So when you multiply by the differential of what's inside the function, you have to multiply by 5. And we'll see what happens here is you're going to have minus 3 times 5, which is going to be minus 15, times minus 4 over 15, times 5y minus 7 to the power of minus 4. And the plus c, of course, becomes 0. They cancel out. You got minus and minus is plus. You're left with 4 times 5y minus 7 to the power of minus 4, which you can rewrite as 4 over 5y minus 7 to the power of 4, which is exactly what we started with. All right, so this is just like, you could say, a check. To make sure that we've done the right thing, you can just check by differentiating what you found and see that it gives you what you started with when you integrated. So that's how you deal with using the reverse of the chain rule. Now, there's different ways that different functions differentiate and integrate. Okay, so this particular one, it's like a bracket to the power of something. You integrate it by adding 1 to the power and dividing by the new power. But certain types of functions integrate in different ways. For example, trig functions. When you integrate cosine, sine x, for example, and you integrate it, you get minus cosine x, and so on. All right, and the function like, do we learn about linear? When you integrate something like 1 over x, you get ln times ln of the modulus of x, and so on. Okay, so we'll go into those. Hopefully, we'll see some examples. But this is just a simple example of integration by reversing the chain rule. Okay, we could also use integration by substitution to do this if you want to. That's perfectly fine. Integration by substitution is basically the origin of doing this, but we recognize a certain pattern that happens when we integrate something like this, where outside the function is the differential or the same order of what's the differential inside it, and this is how it works out. Okay, now for part 2. Now in this question here, part 2, we have a slightly different situation. Although we have like something squared, something to the power of something, it's like you have, let's say you have a function inside another function. Okay, so this is like the 1 minus 4 tan 3x, and the gx is like something squared. Now outside of it, you don't have the differential of what's inside here. Okay, because outside of it you have just a constant. This is like 1 times 1 minus 4 tan 3x squared. Okay, for us to be able to use the reverse of the chain rule, what I should have out here is a differential of what's inside here. So something like the differential of tan of something is the secant of something. So something like secant squared of something. So that should be something like secant squared of 3x 1 minus 4 tan 3x squared. It should be something, some constant times that. Okay, if it's of this form, then I can use the reverse of the chain rule. Why? Because outside the function is the differential of what's inside it. Okay, inside the main function here is something squared. Inside it is 1 minus 4 tan 3x. Outside of it should be the differential of what's inside this for us to use the reverse of the chain rule. So in this case, I cannot use the reverse of the chain rule as I did in the previous part of this question. Okay, so that cannot be done in this case. So in this case, we have no choice but to basically, I guess, expand the bracket and then try to integrate each term individually and hope to see if we will see if I'm assuming that all the terms you get will be terms that we are able to integrate. So if we expand this bracket, you're going to have 1 squared, which is 1. Then you're going to have, it's a squared bracket, so we can use a pattern where you multiply these two together. That gives you minus 4 tan 3x, and then you double it. So that's minus 8 tan of 3x. And then you square the last term. That gives you plus 16 tan squared of 3x dx. Now, if you're not sure how I got that, I'm just going to, for those of you who don't use or are not used to this pattern method of expanding brackets, we know that 1 minus 4 tan 3x squared is equal to this. You just multiply it by itself. So 1 times 1 is 1. 1 times minus 4 tan 3x is minus 4 tan 3x. Minus 4 tan 3x times 1 is minus 4 tan of 3x. And minus times minus is plus. 4 times 4 is 16. And tan x times tan x is tan 3x times tan 3x is tan 3x all squared. Tan of 3x all squared, which is actually the same as saying tan squared of 3x. Okay, so there we have the expansion 1 minus 8 tan 3x plus 16 tan squared 3x. So that's where this expansion comes from, in case you're not used to using this pattern. All right, so we've now integrated, so we've now expanded this, and now hopefully we'll be able to integrate all of these terms. Now I can see that we're able to actually integrate each of these terms, one of them here by modifying it a little bit. So I'm going to write them all separately. So I've got the integral of 1 with respect to x is just x. That's pretty simple. The integral of minus 8 tan 3x with respect to x, I'm going to write it like this first. Negative 8 times the tan of 3x with respect to x. Now, we have a result in the formula book for the integral of the tan of something. Okay, there is a result in the formula book for this. Okay, and you could, in this exam, in an exam like this, you can go straight for the formula book and take that result and use that result. And it's perfectly, absolutely fine for you to do that. However, there are sometimes questions where you are asked to basically prove or show that the tan of something integrates to give you what it's going to give you. All right, so I'm going to show you. Let's get the result first, then I'll show you how to show the result in case you get a question like that. Okay, because this is not just answering the questions here. The point of these videos is to explain to you, how to deal with exams and concepts. So I'm going to show you how to prove that the integral of tan of something becomes what it is. Okay, so I'm going to show you that in a minute. Okay, so we can see if we go to the formula book, which is over here, for P3, it gives you, these different things. Now there's differentiation, okay, from which we can actually deduce some of the results that we need as well. And we have integration. Now they've told us here that the integral of tan x is ln of sec x, ln of the modulus of sec x. So that's what we need to you see, this is f of x, and this is the integral of f of x with respect to x. So the integral of tan x is a ln of secant of x, ln of the modulus of secant of x, all right? So what we're going to do is we're going to show you how, it becomes that, okay? So I know, I'm going to write the result first and then show you how we got this. This is going to be minus 8 times ln of the modulus of secant of 3x, because we've got 3 here, okay? And then I've got to divide this by 3, because you have to divide by the differential of what's inside the function. Okay, when you're differentiating, so when you're integrating something like this, there's a function inside this function, so you have to divide by the differential of what's inside the function. Okay, so you have minus 8 ln secant 3x over 3. Now, how did we get that result? So let me just show you, for example, for tan of x. The integral of tan of x with respect to x. How do we get this result? How do we show that it becomes the ln of secant of x? Now, what we do is we first of all rewrite it as, using the identity, the tan of x is equal to the sine of x over the cosine of x, using one of the very fundamental trig identities. The tan of an angle is equal to the sine of the same angle over the cosine of that same angle. And then we can use the reverse of the chain rule again, all right? Reverse of the chain rule, because what we have here is you have the integral of sine x times 1 over cosine x. Okay? Or you can think of this actually in a better way, as this is like the numerator is the differential of the denominator. Okay? The numerator is of the form of the differential of what's in the denominator. So something like that will always differentiate or integrate to give you the ln of something. So this is going to be sine x times the ln of the modulus of cosine x. The integral of 1 over cosine x is the ln of the modulus of cosine x divided by the differential of what's inside the function, which is, if you differentiate cosine x, you get minus sine x. You get minus sine x. Okay, when you differentiate cosine x, you get minus sine x. Okay, so now what that leads us is, these cancel out and you're left with minus ln of the modulus of cosine of x. All right, now, how does this become secant x? Well, we know that with ln, we've got the power law. This is like ln, the modulus of cosine x, the power of minus 1, using the power law. This is minus 1 times this, so that becomes a power up there. And this means the reciprocal of cosine x, and the reciprocal of cosine x is secant x. The reciprocal of cosine x is, this is like 1 over cosine x, which gives you secant x. So that's how this becomes that. Now, as I said, you don't in this question have to show this at all. You could go to the formula book, look at that result, and then use that result as we did here. Like we just used that result, that you got tan of 3x when you integrate it, becomes ln of the secant of 3x, but then divided by the differential what's inside the function, which is 3. And you had the minus 8 from the outside. So this is how that integrates. Okay, so that's that first part. I'm going to get rid of this now. I just wanted to show you the reason for it. Okay, and then we have to integrate the third part, which is this part, the integral of 16 tan squared of 3x, which I'm going to write as 16 times the integral of tan squared of 3x with respect to x, of course. Right, now, again, we can use the formula book for this. If we go to the formula book and we look at the differential part, we see that secant squared x is the differential of tan x, so the reverse is true. If I integrate secant squared x, I'm going to get tan x. Okay, so that's the basic thing you can see from this this particular problem here. Now the problem is we don't have secant squared x. We have tan squared 3x. We don't have secant squared 3x. So tan squared 3x, I can't integrate it like this because this is not squared, this is squared. What I know is that the integral of secant squared x is equal to tan x. Okay, that's what I know. All right, so if I can rewrite this in terms of secant squared x, then I'll be able to proceed. Okay, so we can't actually use any result for this right away because there's no result for this directly. However, we can rewrite this so that's in terms of secant squared something, and secant squared something integrates to give you the tan of that same thing. All right, so for example now, I know that sine squared theta plus cosine squared theta is equal to 1. That's an identity that we know. All right, if I rewrite this identity as a reciprocal identity by, for example, dividing by cosine squared theta, if I divide each of these by cosine squared theta, I end up with tan squared theta plus 1 equals secant squared theta. So I can say that tan squared theta is the same as secant squared theta minus 1. So I can replace tan squared 3x with secant squared 3x minus 1. So I can rewrite this as 16 times the integral of secant squared theta minus 1, sorry, not theta, 3x, because this is in terms of 3x. Secant squared 3x minus 1 with respect to x. Now I can integrate this, okay, because we know that the differential of tan x is secant squared x. That means the integral of secant squared x is tan x. So now I can say this is 16 times, and this part's going to give me tan of 3x divided by 3. Why? Because you divide by the differential of what's inside the function, minus the integral of 1 is x. So I now have this part integrated. Okay, so this is going to give me 16 over 3 times tan of 3x minus 16x. So now I'm going to put them all together. So I can say that the integral of what we started with, which is 1 minus 8 tan 3x plus 16 tan squared 3x 16 tan squared 3x with respect to x is going to be, well, the integral of 1 was x. So you're going to have x. Then the integral of minus 8 tan 3x was minus 8 over 3 ln times the modulus of the secant of 3x. And then we had this part here, the integral of 16 tan squared 3x gave us plus 16 over 3 tan of 3x minus 16x. So when we simplify that, we end up with, you end up with 16 over 3 tan of 3x, okay, minus 8 over 3 ln of the modulus of secant of 3x, and x minus 16x is minus 15x, and don't forget at the end the plus c. So there's the answer to this question. You must put the plus c at the end. We could have put plus c in each of these, but put plus c at the end to show that you have your constant of integration. All right, so that's a question where there's a few different types of things going on, but what we realize is it's not the type of question where we can use the reverse of the chain rule. Why? Because outside the function is not something of the form of the differential of what's inside it. Okay, and the reason why we could, in fact, here, as I said, we just used the result, but we started off with the sine of x over the cosine of x. When you integrate that, this is the form of the differential on top of what's underneath, so you can use ln here. So this becomes sine x times the ln of cosine x divided by the differential of what's inside. So that's how we dealt with that. And there we have our answer to part 1 and part 2 of this question. So this is some stuff on integration which is in the P3 specification now. With integration, something that we should know, and it's good to practice this. Before in this, you won't find this in the old C3 papers. Okay, you won't find this in the C3 papers. If you practice lots of C3 papers, you won't find any integration in there, because before it was purely in P4. So now you have it in in the new P3. So you must make sure that you do revise it. If you finished all the P3 papers, that's why it's a good idea to go through the C34 papers, so you get exposure for these type of questions as well. Okay, now the next part of the question, which is 12 part 3, is to do with integration by substitution. I'm going to answer that, but I'm going to include that in the P4 material, so I'll make a separate video for that. So other questions that you might want to watch from this particular paper here, I will collect all of them together in this playlist. And questions that you want to watch, which are to dealing with integration from the P3 syllabus, can be found in this playlist over here. And you can subscribe to my channel by clicking on this link. Thank you for watching, and see you soon.